Let's now look at the relationship between complex numbers and polynomials. Now, I mentioned this when we were looking at quadratics before, but it's true for any polynomial. If all the coefficients are real, then the roots or the solutions will appear in conjugate pairs. So that means every polynomial of degree n can be factorised as a mixture of quadratic or linear functions. Okay? That's over the real numbers. And that's because some quadratics can't be factorised using real numbers. But now when we're talking about complex numbers, we can now break it down to n linear factors. Because that quadratic, which before was unsolvable, is now solvable. And we can turn that into 2 linear factors. What it therefore means is every odd-ordered polynomial must have a real root. Because if they're going to appear in pairs, you've got an odd number for the order, then that missing extra one can't be imaginary, or its conjugate would be there. So therefore that missing one, that extra one, has to be real. Means every odd-ordered polynomial must have at least one x-intercept and things like that. All right, so let's just look at this simple one. X squared plus 2x plus 2, which in the past we would have said, oh, that doesn't factorise, but now we know it does. I'll create the, sum of 2 squares in this case. But in reality, it's the difference of 2 squares, because that one that I'm looking at there is actually minus I squared. So we get x plus 1 plus I, x plus 1 minus I. So every quadratic can now be factorised down to linear factors. So if I have to factorise z to the 4 plus z squared minus 12, a quartic. Actually, this one looks like a quadratic, because they're going down by even amounts, so I could do that. Is that going to be quick? Multiplies together to give negative 12, adds together to give 1. It does indeed. Okay, so we've got z squared minus 3, z squared plus 4. Yes, I could go and solve that now, because remember it is equal to 0. Let's pretend we can't. And go, oh geez, I need to factorise that some more. Z squared minus 3, that's fine. Z plus root 3, z minus root 3. And before we would have had a problem with this z squared plus 4. Oh no, what am I going to do? But now we know about complex numbers. So if I was just dealing with real numbers, that's as far as I could go factorising. But now with complex numbers, that z squared plus 4 can be factorised, z plus 2i, z minus 2i. And our solutions, of course, then become plus or minus root 3, plus or minus 2i. So, remember our factor theorem. If x minus a is a factor, then polynomial a will be 0. If it's not monic, say you've got a factor of ax minus b to prove that one, then you sub in b divided by a. So let's factorise 2x cubed minus 3x squared plus 8x plus 5. First thing I know is it's a cubic, so it must have a real solution. So I'll look for that first using the factor theorem. This one's nice because 5 is a prime number, so we're only looking at 1 and 5. Mind you, you got 2x cubed, so it might be a half, it might be 5 on 2. Or what shall we try? Yeah, minus a half makes sense, doesn't it? Okay, let's try minus a half. Oh, it worked, excellent. Gee, that was lucky. So we now know that 2x plus 1's a factor. We can complete the factorisation, whether it be by a polynomial division or inspection, however you do it. And the other factors are quadratic. Multiplies together to give 5, adds together to give negative 2. So now we need to use complex numbers. So completing the square there, we get x minus 1 squared plus 4. So I know it'll be x minus 1 minus 2i, x minus 1 plus 2i. Okay, a quartic, we'd be told there are 2 rational zeros. Find them and then factorise completely over the complex field. Well, rational numbers are real numbers. So again, I could use my factor theorem. 3 is a prime number, excellent. So either 3 or 1, but we've got 4 out the front, so it could be over 4, it could be over 2. Logical first pick. Yeah, half, of course. Oh, good, that works. Yeah, so there's a 0. So I know 2x minus 1's a factor. Then I can look at this and go, well, right, what multiplies together? Yep. So leading term times leading term gives me leading term. Constant times constant gives me constant. What shall we look at? The x's or the x squareds or the x's? Doesn't really matter. At this stage, if I was to leave it like that, I'd have 6x. I want 1x. How do I get from 6 to 1? minus 5. So therefore that minus 1 must have been times 5x. All right, let's now try, what shall we go for?
X cubed.
X cubed, okay. At this stage we have negative 2. You said 2. So this stage we've got minus 2. We want 8. How do we get from minus 2 to 8? Add 10. So therefore, we must have plus 5x squared there. Okay. Oh, boy, now I've got to find the factor of 2x cubed plus 5x squared plus 5x plus 3. Oh, yeah, minus 3 on 2. That makes sense. Yeah, let's go for that one. And, oh, works. Excellent. Okay. So we now know 2x plus 3 is a factor. So I know those two rational zeros that asked me to find were a half and minus 3 on 2. So let's keep going. We've got those two factors. Okay, I'll go leading term times leading term. How many x's do we have at the moment? Oh, it's hard. 4, you reckon? Okay, for those who need a hand, 1 times 3 times 2, 6x. Okay, we got 4. That means negative 1 times 3 times something is negative 3. 1. Oh, there you go. So x squared plus x plus 1. Now let's factorise that. Voila. Now, just a note on this, by the way. Notice, I hate fractions, but it is what it is. I can't. Yeah, it is. I can't multiply by 2 because if I did, I'd be changing the polynomial. If it was an equation, however, I could. Because if it was equal to 0, multiply the left-hand side by 2, multiply the right-hand side by 2, same equation. So, yeah, if it's just a polynomial, we just got to live with it. We have been told it has a real root of multiplicity 2. Multiplicity 2. A double root. What do we know about double roots? Differentiate it. Well, first of all, let's get some ideas. Must be a divisor of 45. 1, 3, 5, 9, 15 and 45 are all possibilities. Thank goodness it's monic. So the derivative, there it is. Oh, well, 1's not working. Damn, that would have been nice. 1's always an easy number to substitute in. That's no good. 3. Oh, phew. Didn't have to go too far down my list. But that's of the derivative. Remember, it has to solve the actual polynomial itself. Oh, good. That works. We've found our double root. So we're dealing with z. Z minus 3 squared is indeed a factor. Now we're going to solve our equation. Z minus 3 squared times something. Leading term times leading term. That one's easy. Constant times constant. We've at the moment got 9. 9 something is a 45. 9 5s are 45. You are right. How many z's do we have at this stage? That's right. Yes, very good, very good. Minus 30.
Oh.
How many do we need?
Minus 30.
Excellent. We're done. So now we just need to factorise the quadratic. Z minus root 5i, Z plus root 5i, and solve. I suppose technically, here's a good point though with a question like this. I didn't actually really need to factorise that because the question didn't say factorise, it simply said solve.
What?
See, look, solve. See that word there? Solve. And so I could have just used the Z squared plus 5 and solved that. But anyway, there we go. Z equals 3 or Z equals plus or minus root 5i. Okay.